addition, um, in addition, so I work with ultra high energy particles, which I will tell you about someday or in the during this presentation, and neutrino. So and also I'm very much interested in machine learning in high energy astronomy. I work with many collaborators all around the world, and in Nepal, uh, some of us are there are my strong collaborators in Nepal. For example, I'm Dr. Niraj Dital huनुहुन्छ. Similarly, I'm also working with Yagesi on X-ray actually observations, and other students also. And टेक प्रसाद अधिकारी हुनुहुन्छ, उहाँसँग पनि धेरै पब्लिकेसन 3-4वटा पब्लिकेसन हाम्रो कतिवटा भइसक्यो, कतिवटा हुनेवाला छ. So this is my team, and that's what I work. So today I'm going to present an overview of an X-ray astronomy, which is a very important component of multi-messenger astronomy. So let me start by the the traditional astronomy, which mainly uses electromagnetic radiation. As you may all know, the traditional astronomy mainly started from visible light, right? They pointed out the first time, Galileo pointed out the telescope at the moon and then Jupiter and those kind of it all started with the telescope, the conventional telescopes, and later where there are big telescopes and so on. But what you have to remember is the electromagnetic, the spectrum of electromagnetic radiation. In that spectrum, the visible is a very tiny fraction, as you can see in this plot. So a typical electromagnetic spectrum would range from radios to gamma ray, right? So starting low frequency radios and infrared, and then optical, which is zoomed in invisible light, and after that going towards higher frequency, the ultraviolet, and then X-ray, and then gamma rays. So that's so there's some a little bit of introduction how they are used in practical uses. So in the plot below, you can see that the radio waves are mainly used for radio and television, and then microwave. This also is a part of radio frequency, and infrared. All the heat we receive from heater or the sun, that falls within infrared, and you're familiar with the visible, all these red, blue, green, the rainbow colors that's visible, and ultraviolet, that's used in fluorescence tubes, that bulbs white light, and then X-ray. You're familiar of the medical uses of X-rays, and the energetic photons, which are even more energetic than X-rays, are gamma rays. And gamma rays are for medical purposes, it's mostly used for killing cancer cells. So that's a brief introduction on the spectrum of electromagnetic radiation. And here is an interesting quote by one of philosopher, 18th century philosopher, 1890s, who said that that the stars are so distant that we will never know how the stars are made of their chemical composition. He said that this is very far away, we can see them, but we will never know the chemical compositions. And the next year, the astronomers or scientists developed the spectrometry, a way of finding the chemical composition. And the next year, then then we know that we can actually fairly know what the stars are composed of. That's very very interesting historical context. All right, so we would like to observe a system like a black hole system or any astrophysical system through telescopes that can look into several bands of electromagnetic radiation. Right? We will, as I told, we would like to see it in radio, in microwave, in infrared, and gamma rays and X-rays. But the question is, can we observe them from the surface of the Earth? This is the question. And the answer is for some of them, yes, and for some of them, no. So you can look at this plot, and this shows the transmission of the electromagnetic waves, different kinds of electromagnetic waves, lights, through our atmosphere. So if you start from the low frequency waves, so very low wave frequency, do not the atmosphere, the Earth has atmosphere, we does not transmit the very long radio waves. And then comes the radio window, which we can observe actually from the surface. And for that, we built giant dishes to see the universe in radio. And then, but the atmosphere also contains some water molecule, and which absorbs the microwave. So we again cannot see the universe through microwave. So we will have to fly planes will evolve a certain height in the atmosphere, or space telescopes, and then infrared. So and then after that, visible light we can see from surface. So that's how with the telescope point out to the universe. But again, we cannot see the ultraviolet and X-rays and gamma rays. These are mostly blocked by the atmosphere, so we will not have a good view of the universe if you have a telescope on the surface of the Earth. So the question is, so that's why we need the space observatory, meaning we have to put the telescopes on space. Why? Because we have a atmosphere and which absorbs some of the lights, and basically this is opaque to X-rays and gamma rays. So this is one of the need why we have to put the X-ray telescopes in the orbit. All right. How the X-ray mirrors work? This is a basic principle. Now, the first thing we have to understand is it doesn't work the same way the optical telescopes work. So here I show you the basic principle of optical telescopes. The parallel light rays pass through the lenses, and they focus at some point. This is how the optical telescopes works. But for X-ray, it doesn't work. Why? It's for a simple reason that X-ray can penetrate the transparent objects like glasses or lenses. So how they're constructed? They are constructed with metals, nested mirror. They're nested one on top of another. You can see this figure, and they work by the principle of total internal reflection, which you know that when light passes from rare to denser, denser to rare, sorry, and then if you pass some critical angle, then it reflects back, and which is called total internal reflection. So in the similar way, in the nested loops, the X-rays are sent as a grazing incident, and then they reflect back. So and then where you can bottom down, you can see the focus, how these X-rays can be focused. Okay, this is the so for X-rays, the lenses are quite different from the ones for optical telescopes. All right. How does the universe look if you look through an X-ray telescope? and this is what you see. Okay, this is the all sky scan map for one of the modern X-ray telescope known as Eurosita by ESA, European Space Agency. And excuse me, when you look through this telescope, that's what you see. So the first thing, very obvious, is the galactic plane. You see that line, yes, that's galactic planes. And besides that, there are some bright sources, something like Crab pulsar or Orion Nebula. You can even see, and the Vela SNR supernova remnant, which you may know, and we may also talk about that later. And SCUX1, there's a bright X-ray source, binary, actually X-ray binary source in Scorpio constellation. So these are the kind of things when you and which is a bit entirely different from what you see in the Hubble images. You know, when you look um, through the optical telescope. Now, I would like to start with a brief history of how X-ray astronomy came about. So in 19, after the Second World War, there were lots of left out rockets, and what they did was they put the detector and then flew the rocket up, and they first detected the solar corona, the strong X-ray emission from solar corona. And things progressed, and in 60s there were something called aerobee rockets, which were not put in the orbit, but they were flown, and they would fly some height and ascend and reach some height and descend down. And during that brief travel period, there will be X-ray, spinning the detector, and I will try to see what's the strong X-ray. And that's how the Scorpius X1, SCO X1 for short, was discovered in those period. And later it came to be known as the binary system, in which one of the source is a neutron star, and the other is a normal star, which was going around, and there was accretion system. And then later came the orbital telescopes. They were able to put the space telescopes in the orbit, and they discover many more sources of X-rays, like the supernova remnants, M87 and Cygnus A, and other clusters, pool of galaxies. X-ray facilities over the years. So in 1960s, there were the flying rockets. For briefly, they were not put into the orbit, and later they were put into orbits, and 70s, in mainly 70s, 80s. There were collimators. Something called a collimator is basically kind of pipe where you have to resolve some individual sources. You can do that with collimators. And then later there were sophisticated instruments, something like called Einstein Observatory, and Exosat by European astronomers, and then the even advanced type of detectors like Chandra and XMM Newton and new stars. So they slowly evolved over the years. So that's the brief history of how X-ray instruments evolved over the years. So one of the early objects. So the first thing they notice when they look through the X-ray detector or telescope, they're basically detector, but we can call them telescope. The first saw the corona, solar corona, and after that the first extrasolar source, strong, which emitted strongly in X-ray, was a SCUX1, and that means which is an object in the constellation Scorpio, Scorpius, and you can see this. This is the plot from the 1967. So they were looking into, they were slowly sweeping the telescope along the galactic plane, and you see that, uh, um, and in y-axis, so in x-axis what you see is a scan angle. They were slowly scanning an angle, and what in y-axis what you see, the count rates, in X-ray count rates. Yeah. So around 200, see around 200, between 200 and 220, you see a sharp rise in the counts, and was that SCOX1. And in optical, that later they found out is a tiny dot to the left. You can see that. So that was in late 1960s when they first found out an astrophysical source, which was extra solar object, which was a strong X-ray emitter of X-rays. And they also looked at into the moon. So this is what you see when you look through an X-ray telescope. Moon. You see that. So there are three distinct things you can see. The first thing you can see is the diffuse X-ray background, something like CMB, yes, cosmic microwave background. So meaning that's all pervading X-ray uh, mm, diffuse background, and that's what you want to see. The other thing is you see the bright side of the moon, right? That's lit by the sun. Actually, this is the moon doesn't like in case of optical. The moon doesn't have its own source. It doesn't emit X-ray by itself. So what happens is the very energetic particles from the sun come and hit the lunar surface, and they emit X-rays. That's how you see the bright side of the. Besides, you can also see the shadow, and there are some X-rays. This can be due to the very strong winds from solar winds that hit the other side of the moon and then produce X-rays. That's possible. This image was taken in 1990. So that's the moon if when you look through an X-ray telescope. Um, some of the current X-ray observatories which are widely used are XMM Newton, Chandra, and Swift Observatory, and New Star. And um, I and with my colleagues, including in Nepal, we have also used some of the observatories for our own research in AGNs, active galactic nuclei, which I will tell you more about later. So let me go over these instruments briefly. So Chandra is one of the impressive instruments with unprecedented resolution and spectral precision. The response time is 15 microseconds, which can be very useful to detect the pulsars. You might know what pulsars are. I can also talk about later. So uh, it was very important in the study of the universe in X-rays, uh, like many things, pulsars and supernova remnants, uh, even sun and moon. And one of the impressive discovery, it has many important discoveries, but because I don't have much time to go over every one of them, I just want to like point out one thing. So here what you see is a collision of two galaxy clusters. You can imagine, yes, there's a galaxy and there's a galaxy cluster, and they sort of form a binary systems. One pool of large galaxies in one side, the other side, and they collide. And what happens when they collide, the gas above them hits to the millions of degrees, and that then emits these the X-rays. And in the figure, what you see is this kind of reddish or is X-ray, yeah. This is famously known as bullet cluster, and this kind of reddish is the color of X-rays, and bluish. You can see that there are two distinct clusters which underwent collision, and this one to the left and one to the right, and this blue is the what they uh, call dark matter, as they mapped from the gravitational lensing. So so what we now know is that the dark matter is probably with the galaxy, yeah, not like gas which is everywhere. So on contrary, the gas is like in between the galaxies, two colliding galaxies, which got heated by again by a collision, and that's what you see. So these are one of the important images by Chandra. And the other one, very famous by ESA, which launched in 1999, which is nearly 25 years old now, is XMM Newton. So it operates into 0.5 to 12 keV. That's how in X-ray the frequency is expressed in terms of kiloelectron volt. You know, you can convert a frequency by h nu to the energy, right? And that's the waveband. And this is very sensitive instrument, and it collects 5 times as much as uh, Chandra collects photons, 5 times. Very, very sensitive images. And but this is mainly spectral and timing analysis. The Chandra is used for imaging purpose, but this one is mainly used for timing and spectral um, uh, analysis purposes. So it detects many, again, galactic sources and extragalactic sources. So one of the picture what I show you is again a galaxy cluster 9 billion lights far away. And this purple, this is actually composite image of the Chandra and the Hubble. The X-ray is shown in purple color. And again, these are the the gas plasma that are heated in the deep potential gravitational potential wave of the cluster. And we have also worked in using this telescope. Some of our work, for example, involved again Nepali colleagues. Some of our publications, Mohorin 2020 and Dinesh 2030, and these also involve a large number of Nepali collaborators. The other one is the Swift telescope, recently renamed as Neil Grahel, one of the first contributor to this telescope. And it was built mainly purpose of the GRBs, which is gamma ray burst. You might know gamma ray bursts are one of the fascinating transient astrophysical phenomena, very cataclysmic, meaning um, in few seconds, you just see a few seconds of gamma ray flash, which is very, very bright, brighter than the whole galaxy, and it's gone away. And what you can see is something called afterglow, and then you can it's visible. So first gamma ray flash for a brief period, and then follows the X-ray and the optical and UV, which you can monitor for a few months, and then completely goes away. The GRVs are very interesting, and they can emit their luminosity that's emitted in a few seconds is comparable to the solar luminosity over its entire period, right? How much sun can emit during its lifetime is emitted in a brief flash during a brief second. So they are thought to be there are two models of the RBs. One is the two neutron star colliding. The other is the supernova, and collision. The inner when there's a supernova, and the rest of matter falls back, and there's a huge energy production, which is in terms of this produces the jets and gamma ray flashes, and later the ejecta comes to the is thrown out into the space, and there are shock waves and all kind of things. Very interesting sources. Um, and this Swift has mainly three instruments. One is BAT, something called burst alert telescopes, which detects something called prompt emission, and then the energy of the emission kind of decreases. So you can see in XRT, which operates in 0.2 to 10 keV, and also there's a simultaneous UV and optical telescopes that operate between 170 to 65 nanometer wavelength. And so it's basically multi-wavelength instrument. You can see what's going on at the same simultaneously in different wave bands. So we have also worked into this use these telescopes and worked into the GRBs. You can see Dynity et al. 2003. We have our publication. And New Star. There's a fairly recent, very modern hard X-ray instrument, which has not one telescope, kind of two eyes, two telescopes together, and it was launched 2012, fairly recent. The wave band 3 to 79 keV, and it doesn't have a very great angular resolution, but it looks into the hard X-ray, something called hard X-ray. For example, if you look sun through this telescope, it would look something like this. Um, and then it also looks into the Asian systems. The Asian has a central black hole at the center, and it's surrounded by a huge accretion disk. Excuse me, there seems to be some messes. I'm sorry. Is there any message from me? For me? Oh. All right, let me know the time, please. No, I'm not.
Yes, sir, go ahead.
I'm not tracking the time, so please let me know. Okay, whenever I have to stop. There's so much things in X-ray, but all right. So I was saying that New Star can look into the sun or the distant Asian systems, active galactic nuclei, which is housed by supermassive black holes, accretion disk, and relativistic jets. Is a fascinating extragalactic objects. We also are involved into study of these Asians using different kinds of space and ground-based telescopes. For example, one of we also use these telescopes and studied on a large number of blazars. And so in 2028, 18, we have a publication using this telescope. So now the question is, in the context of X-ray astrophysical systems, how X-rays are produced? This is an important question, right? What can they tell? For which processes can produce X-rays, and what can you know about the conditions, the physical processes in astrophysical context? So for that, we have to understand how they are produced, all right? So they are produced in astrophysical context. They're produced in a number of ways. The most important of them is something number one, thermal Bremsstrahlung emission, which I'll a little bit describe in next few slides, and famously synchrotron radiation, and inverse Compton emission, and line emission, X-ray line emissions. If you are BSc students, probably you know some of them or all of them, but let me briefly explain them. So in hot plasma, like in accretion disk or deep potential gravitational potential well, so the gas is heated and then they are in the form of plasma. So the electrons are constantly moving around. They're heated because like and they occasionally pass through the protons or electrons. And what happens is their trajectory is changed. They're deflected by the electric field of protons or other uh, um, ions, right? In that case, X-ray is emitted, when they're, because deflection is kind of acceleration or deceleration. Whenever the electrons are decelerated, there is a electromagnetic emission, and in this case, they produce X-rays. Okay, and this way, the plasma can be 1 to 10 million Kelvin. So you can see. So X-ray, basically, in thermal sense, this is thermal Brentzlow. This is non-thermal. I'll explain it in the next slide. So when you see the X-ray coming from some system which you think resulted from thermal processes, then you have to know that you are exploring, probing a very hot surrounding processes that can be from 1 to 10 million Kelvin. Okay, that's the, for example, sun's corona or Asian accretion disk or things like that. They are that hot, 1 to 10 million Kelvin. So that's the thermal generation of X-rays. So in non-thermal, so non-thermal meaning so you do not hit them. Yeah. So it's famous synchrotron radiation. Yes. So what happens? The electrons or the charge are accelerated in shock waves, and they're very energetic, and they plunge into the magnetic field. And when you do that, they emit the X-rays, and what wave band they emit is proportional to their energy. Yes. And in for X-ray, for charges to X-ray emit X-ray, they have to be very energetic. The Lorentz factor is compared to million, yeah, 10 to the power 6 or 10 to the power 9 to up to billion. So if this much energetic particle plunges into magnetic fields, they emit, and that's how the jets, basically the relativistic jets. So here I show you the M87 in optical to the left, and to the right, this is the Chandra image of the jets of M87. And in jets are there shock waves, and the shock waves turns the particle distribution into power law, and this power law signature and the power law distribution of electrons or charged particles translates into the power law spectral spectra of emission, and those mostly happen into the relativistic jets, that can be in Asian or galactic systems like binary black hole systems. There can be something called microquasar. So this is the non-thermal source of the X-ray. So the other way is the inverse Compton scattering. Yes. So what happens that there are photons and there are energetic particles like electrons. So electrons are very high energy, and then they collide with the low energy photons and then up scatter. I'm sure the BSc students know this Compton scattering and then the inverse Compton scattering. And this is how some of the X-rays come from hot spots of Cygnus A. So this is the image from Chandra. You see hot spots, meaning the outer edges. You can see some dot-like things far away from this is the center. This is the center, probably black hole, supermassive black holes. And this is the diffuse X-ray, the surrounding. And then you see two bright prominent dots, and which are when the shock wave hits the intergalactic medium and produces a lot of X-rays. So wonderful, fascinating things and like that. So in rest of things, you see a diffuse background. So what happens that there's CMB, see, there's CMB is everywhere, micro cosmic microwave background, and then there are very energetic electrons which are accelerated in jets, and when they hit the low energy photon like CMB, they can up scatter them into X-rays, and you can see these kind of things. Beautiful thing. All right. So that's inverse Compton scattering way of generating X-ray in astrophysical context. And there's another also way is that the line. So famously, um, this 6.4 kV line is very famous. So in atomic transition, you might know the atomic structures and the emission of photon when it jumps from one orbit to another orbit. Um, you see a line emission, and in particular, the iron emission line is the 6.4 kV, and these are very important because the 6.4 is very important in exporting the material near the black holes or in stars because they have this typical 6.4 lines. You see that. And for example, these are real observations of where you can see the spectra, actually, spectra, uh, real observations, spectral observations, and which you can see a bump around 6.4 kV to the left. This is Seyfert 1 galaxy, this is Seyfert 2 galaxy. These are kind of Asian active galactic nuclei. And this, you see bump. That is the signature of the irons, presence of iron in that region. So usually the process by which this gives is something like this. So in accretion disk, there's a black hole, there's accretion disk, and at some um, way up, there's the corona, which is a strong emitter of X-ray, like sun, but many more magnitude than the sun, right? It's a supermassive black hole, like 10 to the power a billion times bigger than the sun's. And there's a strong source of corona, which is shine onto the accretion disk, falls on the accretion disk, and it probes the matter around it. There's iron, yes, and which you can see as a reflected emission. You can see those things, and then you probe how fast this the accretion disk material is going around the central black hole systems, and also if you look very close to the system, black hole, and you can also estimate the spin of the black hole systems using this iron K alpha line, which is at 6.4 keV. Now, but it's not very easy to uh, uh, find about this the 6.4 keV because there could be a number of processes that can be deforming the simple line-like feature. For example, this is let's say we are looking into an annular section of annual section of in accretion disk. Then from Newtonian perspective, it will something look like that because one part is going, you're looking Asian, yeah. So this part is going into and some part is coming outward. So you will see two wings, right? So that the line will be sifted into two parts. One is the incoming and there's outgoing. But then you uh, take into consideration of the special relativistic effects and the transverse Doppler shift, and that will give you an asymmetric shape, meaning the incoming will be stronger, the the going into would be uh, less in intensity. Uh, these things, and on top of that, because there's a strong gravity, they can further shift the frequency and also in intensity. So a single line profile might something like would be distorted in this form in the last what is shown in the last. This is by simulation, and real observation is looks like something like this. You know, um, these are the x-axis is the energy, meaning representing wave bands or frequency, and the y-axis is again number of counts, and then each dot is a count, and this line is kind of fitting. So thus indeed looks like the line profile that's predicted by CA. All right, and this line technique also can be used to measure the spin of black holes. The black holes have uh, mainly three properties, yes: the mass, the angular momentum, and the charge, a little bit of charge. The angular momentum, meaning the black hole can be rotating or non-rotating, meaning spherically symmetric, which is called Schwarzschild black hole. Some of you might have studied. And the other type which has angular momentum is called curved black hole, and these are spinning very fast. And these are very important. Why? Because the spin of the black hole is thought to be the main reason for having the relativistic jets. The microquasars or the blazars have relativistic particles, like which is coming from the black hole bipolar jets, which extends up to megaparsecs, right? You can see them in radio images and X-ray also. I showed you one signal say. So now the question is how the jets are produced in those black hole systems. And one of the widely discussed topic is the spinning black hole, that you extract energy from a spinning black hole, and that results in the jets. So, and then the question is, what you would like to measure the spin of the black hole. So how would you measure that? So through telescope. So again, X-ray telescope, you will go very near to the central region, very close to something called ISCO, right? Innermost stable circular orbit. So ISCO for short, meaning that past this a distance, the radius, the radius of the the uh, the radius of the trajectory of the things rotating black hole become chaotic. They don't follow a particular pattern, but for some distance they are very regularly follow a circular. So these are called ISCO. So what happens is that if there are iron in those ISCO, then you can see the iron lines and this distorted profile. From there, you can tell how fast or slow the black hole could be spinning. So this is very important in the study of black hole spin. Yeah. And another kind of sources they are used to explore, learn about is the supernova remnant. So most of you might know what supernova is. So at the end stage of the cycle of a star, a massive star, there's a big explosion, and and um, the outer layer of the star is cast into with high speed into intergalactic medium, and they form shock waves, and then they keep on expanding for many thousands years, and that is called supernova remnant. The supernova is the right moment when that explosion happens, but remnant is that after many years those gases kind of keep on expanding, and they because they have shock waves and things like that, they also emit in X-ray. So this is what you see in X-ray. This is the uh, Chandra image of two famous supernova remnant called Tycho, named after Tycho and Kepler, and this purple round is X-ray. So these kind of things you can see, and they can help explore this kind of sources. And binary black hole systems that I talked about, these are very important. The stars, a large number of stars live into binary systems. They're not alone. Oh, and it happens that one of the companion is the black hole or the neutron star with very strong spin, and it can tear up the material from the other companion and
5 minutes
form.
more time.
I'm sorry.
5 minutes more time.
Okay. So resulting in something called X-ray binaries, and that was I talked about this Scorpio X1, So and similarly in pulsars, right? So what are pulsars? Pulsars are the neutron stars, which is a large magnetic field, and they have a strong spin. So and they emit jets from their polar, and when it sweeps through the towards Earth, then we see a regular periodic burst, something like I can show you here. Yes, periodic profile of X-ray, and these are called the cosmic clocks. They very precisely uh, um, repeat. So that's important subject of the investigation. Yeah. And starburst galaxies, and the starburst galaxies are the galaxies where there are lots of supernovas around. Because and then the supernova are the signatures of star spurs, because the in supernova meaning the formation, the end of the stars, the one generation of star, and they push the material into intergalactic, and they compress gas, and from there the new generation of star is born. So very important. So there are some galaxies called where frequently this kind of explosion coming, and this is called starburst galaxies. You can see these things. You can also see in spiral galaxies. There's a large temperature, high temperature, meaning there's always X-rays. You can see them in purple. The spiral galaxy in arms, you can see those X-rays. And again in galaxy cluster as a pool, because the galaxy, a cluster of galaxy has a deep gravitational uh, well, and the gas into them is like constantly sloshing here and there, forming a very hot plasma, and then and these are strong sorts of galaxies. And this also potentially probe dark matters, because we really don't know what dark matter is, but one of the models predict that they will have a line in X-ray, like 3 keV. And if you see these kind of things, probably the dark matter is there. All right. So just in the right time, I guess. So thank you very much. If you have any questions, I know if there's any way of asking questions, but I will try to answer if there are questions.
Okay, thank you very much, sir, for your nice presentation and knowledgeable for us. And now, क्वेसन र क्वेरी केही अब जिज्ञासा केही क्वेसन छ भने म क्वेसन राख्नलाई अनुरोध गर्दछु। Any question, any queries? Okay, सर हामीलाई सरबाट धेरै हामीले नलेज यो इन्फर्मेसन र नलेजहरू पायौँ र सुन्ने अझ चाहना हुँदाहुँदै टाइमको लिमिटेसनबाट अरू फर्दर सुन्न सकेनौँ। तर पनि मैले एउटा सरलाई सानो जिज्ञासा राखेँ। हाम्रो हाम्रा अब यहाँका पार्टिसिपेट भनौँ नेपालका विद्यार्थीहरूले के कस्ता अपर्च्युनिटीहरू पाउन सक्छन् र कस्तो किसिमले सम्पर्क गर्नु पर्ला, सरबाट सानो एउटा जिज्ञासा मैले राखेँ सर।
हजुर हजुर होइन, यो नै इम्पोर्टेन्ट हो। साइन्सभन्दा पनि हामीले आफ्नो कम्युनिटी, आफ्नो स्टुडेन्टहरूलाई कसरी चाहिँ जो ज्ञान छ त्यसलाई इन्फर्मेसन डिसमिट गर्न सकिन्छ भन्ने कुरो नै जरुरी कुरा हो। त्यसको लागि मैले चाहिँ अब नेपालमा अब योगेशजी पनि हुनुहुन्छ त्यहाँ। हामीले यो एक्सएमएम न्युटन भयो, अनि जति पनि मैले जो स्पेस टेलिस्कोपको केही कुराहरू गरेँ, त्योहरू हामीले त्यसको डाटा लिएर काम गरिरहेछौँ। त्यो त्यो हाम्रो नेपालमा अब निरजी हुनुहुन्छ, जस्तो योगेशजी हुनुहुन्छ, केही भाइ बहिनीहरू हुनुहुन्छ। त्यस कारणले यहाँहरूलाई इन्ट्रेस्ट भयो भने अब यो स्पेस टेलिस्कोपको डेटाहरू चाहिँ फ्रिली पब्लिकली एभाइलेबल छ। पहिला तपाईँहरूले के विचार गर्नुपर्ने, तपाईँलाई कुन कुरामा इन्ट्रेस्ट छ? तपाईँलाई ग्यालेक्टिक ब्ल्याक होल सिस्टममा इन्ट्रेस्ट छ कि पल्सारमा इन्ट्रेस्ट छ कि ब्लेजार अरू एजियनमा इन्ट्रेस्ट छ? पहिला त्यो पहिल्याउन भयो भने त्यसपछि हामी कुनै पनि एउटा इन्स्ट्रुमेन्ट युज गर्न सक्छौँ र डेटा चाहिँ पब्लिकली अभाइलेबल छ। अब डेटा पब्लिकली अभाइलेबल भन्नुको मतलब चाहिँ फेरि के हुन्छ भने सिधै युज गर्न सकिने डेटा हुँदैन, त्यसलाई प्रोसेस गर्नुपर्छ, किनकि अब स्पेसले टेलिस्कोपको डेटा त अर्कै फर्मेटको डिजिटल फर्मेटमा हुन्छ, त्यो हामीले प्रोसेस गर्नुपर्छ। त्यसको लागि केही स्किल्सहरू चाहिन्छ, केही सफ्टवेयरहरू जुन चाहिँ नर्मली विन्डोजहरूमा पनि गर्न सकिँदैन। त्यस कारणले लिनक्स युबन्टूहरूको ज्ञान हुन अलि आवश्यक हुन्छ। र तीबाट चाहिँ हामीले डाटा प्रोसेस गर्न सक्यौँ भने हामीले त्यसको लाइट कर्भ र स्पेक्ट्राहरू निकाल्न सकिन्छ। र त्यसको लाइट कर्भ र स्पेक्ट्राको अध्ययनबाट चाहिँ हामीले अनि त्यो 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 वस्तुको एस्ट्रोफिजिकल सिस्टमको बारेमा केही कुराहरू भनेर अनि पेपर प्रकाशित गर्न सक्छौँ। त्यस कारणले अब त्यहाँ भाइ बहिनीहरूलाई इन्ट्रेस्ट छ भने यु क्यान राइट मी, यु क्यान राइट निरजी, यु क्यान राइट योगेशजी। मैले अघि भने हामीले दुई तिनवटा पेपरहरू चाहिँ त्यहाँ निकालिसकेका छौँ, नेपालीहरू मिलेर है, नेपालीहरू चाहिँ मिलेर। त्यस कारण तपाईँहरूलाई पनि यी कुराहरूमा इन्ट्रेस्ट भयो भने डिरेक्टली तपाईँ मलाई पनि लेख्न सक्नुहुन्छ। यु क्यान सेन्ड मी इमेल ओर योगेशजी और निरजी, जसले पनि सक्नुहुन्छ। हामीहरू त्यस्तो ग्रुपहरू बनाउन सक्छौँ जहाँ रिमोटली काम गर्न सक्छौँ र जस्तो चाहिँ अहिले अब धेरै भाइ बहिनीहरूको चाहिँ इच्छा चाहिँ विदेशमा गएर पढौँ भन्ने, यो विषयमा एस्ट्रोफिजिक्समा पढौँ भन्ने इच्छा होला र जो हुनु स्वाभाविक हो, हुनु पनि पर्छ। नेपालीहरूले धेरै धेरै राम्रो ठाउँमा धेरै धेरै कामहरू पनि गरेका छन्। तर तपाईँहरूले एउटा कुरा बुझ्न के आवश्यक छ भने आजकल यदि युरोपमा, मोस्टली युरोपमा र अमेरिकामा जहाँ पनि तपाईँलाई पिएचडीहरूमा इनरोल पर्नु पर्यो भने तिनीहरूले पेपर खोज्छन् है, यु सुड ह्याभ पब्लिस्ड। अब मेरो ठाउँमा चाहिँ वान क्राइटेरिया, यु मस्ट ह्याभ पब्लिस्ड वान पेपर, वान इन्टरनेसनल जर्नल पेपर, त्यो बिना मान्दैन। त्यस कारणले अब हामीहरूको टाइममा त थिङ्स वर डिफ्रेन्ट होइन, वी क्यानट कम्पेयर। अहिले तपाईँको टेक्नोलोजीको एक्सेसिबल छ सबै कुराहरू भनेपछि तपाईँहरूले लर्न गर्नुपर्ने चाहिँ लिनक्स भयो होइन, अनि अनि लेटेकहरू यस्तो कुराहरू, ओभरलिफमा कसरी पेपर बनाउने, कसरी प्लट बनाउने, कसरी पाइथनहरू, यो सबै सिकेर। सो त्यस कारणले अप्लाई गर्नुभन्दा पहिला यो सबैले धेरै जसोले एउटा पेपर चाहिँ पिएचडीको लागि चाहिँ एउटा पेपर एकदमै मागिहाल्छन् है। त्यस कारणले अहिलेदेखि नै यी कुराहरूको चाहिँ सदुपयोग गर्ने। अब सबै स्पेस टेलिस्कोप मैले भने डाटाहरू फ्री छ, तपाईँले चलाउन मात्र जान्नु पऱ्यो। त्यस कारणले यो कुरा हो। सम्पर्कको लागि हामी योगेशजी अथवा मलाई जसलाई पनि लेख्न सक्नुहुन्छ। आई थिङ्क हेल्पफुल होला भन्ने इन्फर्मेसन जस्तो लाग्छ मलाई।
ओके, थ्याङ्क यू भेरी मच सर। सर धेरै धेरै धन्यवाद सरलाई।
हस् त म
हस् गोपाल सर, धन्यवाद।
हजुर हजुर योगेशजी, ल धन्यवाद, म साइन आउट गरेँ। ए राजेशजी पनि देखिनुभयो।